So hello everyone, this is lecture 19 for the classical physics. In the last lecture we did up to here. We were considering some examples to calculate the degree of freedoms for different systems. Now let's see some more systems. Let's say we have this spherical system and we have 3 beads attached to it of mass small m, and there is spring attached to all of these. Now these 3 beads are restricted to move on this surface of this sphere, means vertical circle, and this vertical circle is rotating, means this is the z-axis and this is rotating like this, and these beads are restricted to move on this circumference only. Now how much number of degree of freedom will be there? So total coordinates will be 3n 3 for each one, minus how much restrictions we have. So constant number of constants will be, you see, every bead, the distance from the center will be r, because it's kind of sphere will be formed when it rotates, the sphere will be formed. So we can see that in spherical coordinates we have r, theta and phi. So this r will always remain constant, and this theta, phi, we have 2 restrictions, means 2 are free and only 1 restriction. For 3 beads we have 3 constants, and total number of coordinates will be 3n. So 3 3 and 9 minus 3 will be 6. So degree of freedom for this kind of system will be 6. We will see that why we are calculating degree of freedom and what is the use of these degree of freedom. Just wait and watch. So for 1D system, we have let's say we have a rod and it is put it on the x-axis and it is only free to move in the x-axis. So this is 1D system. So each means there are infinite number of particles this rod has. So each particle is can be represented in terms of x1, means only one coordinate is required. So only 1 degree of freedom is have, means by 1. See, if you consider second point here, second mass here, then coordinates of this point can be found using the help of this coordinate. So only 1 degree of freedom is required to describe whole this system. So if you have n particles here, then each particle's coordinate can be determined using this coordinate. So only 1 degree of freedom is here for the 1D system. Okay, now what happens in the 2D system? Let's say we have this plane and we have this one particle. So this have 2 coordinates possible, and let's say we have one more particle here. Then how much degree of freedom for these 2? So 1 carries 2, so 2 2 is 4, minus number of constant will be 1, this distance between them. So for these 2 points, 2 mass system, we have degree of freedom will be 2 to the 4 minus 1 3. Now see, if we take third point here, then coordinates of this point can be determined using this and this, because this length is fixed, this length is fixed, and only 2 variables this have and 2 equations we are getting. So now this third one's coordinate can be found using the help of these 2. So that's why you see that now degree of freedoms will be 2 3 6 minus 3 constants will be there, and it is again 3. So see, if it is 4 5 particles, infinite number of particles, degree of freedom will always remain 3. Okay, hope you get the point why it is always 3, because with the help of these 2 we can find the coordinates of any number of particles. Same as using this single particle we can find the coordinates of any number of particles. That's why degree of freedom was 1 here and 3 is here. This happens in the 3D system where you remember, then you can, there the least number of particles required was 3, means any fourth will be found using that 3. We already discussed this case here. Why it is 6, means only 6 are required degree of freedoms for the 3D system. So for a d dimension system, you can directly find the value. Degree of freedom will be 1 upon 2 d plus 1, where d represents the dimension, means 2 for 2d it will be 2 plus 1 3, and it will be 3. For 3 it will be 3 plus 1 4, and it will be 6. So that's how you can find the degree of freedoms for different kind of systems. These are rigid systems. Now let's see one more. This is a double pendulum. What the double pendulum means, one pendulum is here and second is attached to this pendulum. So we have 2 lengths, and so let's find the degree of freedom for this kind of system. See, each mass required 3 coordinates, so 3 for this, 3 for this. Now how many constants we have? See, this length is fixed, this length is fixed, and it is restricted, whole pendulum is restricted to move in the xy plane. So z coordinate will be 0. For this one, z1 will be 0, z2 will be 0, and this length is L1, this length is L2. So we have 4 constants here. So 3n minus 4, so n is 2 mass we have, so it will be 6 minus 4, that will be 2. So degree of freedom required for this kind of system will be 2. Now let's say we replace this wire by a spring, then how many degree of freedoms will we have? So see, if you remove this with a spring, then this length will change with time. This is a constant, but this won't be have the ability to reduce the one of the variable. So only constant which will reduce the variable will be this length, and the z1 equal to 0, z2 equal to 0. So we'll have only 3 constants here. So total degree of freedom will be 3 of 6 minus 3 is 3. So this will be 3 degree of freedoms will we have, because this length is changing with time. This is a constant, but this constant doesn't have the ability to reduce the independent variable. So as we already discussed here, so this is just a subset of this. Now let's see some definitions. Now number of degree freedoms we are getting here, these are equal to the number of independent variables we require to define the system, and these are called the generalized coordinate actually. Okay, means the number of degree freedoms we have, we can describe that number of generalized coordinates, and only that much are required. So degree of freedom is 3n minus k. These are the generalized coordinates actually. Is a set of physical quantities which act as an independent variables to specify the position and configuration of systems. All the Cartesian coordinates can be represented as a function of generalized coordinates. Now see, these are the coordinates which can, means these are the number of independent variables which are required to describe the complete system. Means whether there are 3 particles, 4 particles, if you find the total degree of freedom, that amount of coordinates can describe whole the system, because we have find it that coordinates from here, means the number of amount of independent variables. And see, these all Cartesian coordinates can be represented in terms of generalized coordinates. Okay. Function of generalized coordinates, where these are the generalized coordinates q1, q2, q3, and these generalized coordinates are equal to the degree of freedom, n equal to 3n minus k. So we need only n generalized coordinates. So you will see more when I will tell you that how interesting and useful they are. So, and these generalized coordinates can be any physical quantity. They don't need to be distances only, means in the real space, you know, we describe only the x distance, y distance, z distance. But here these generalized coordinates can denote, can describe even velocity, temperature, any physical quantity you can describe on them. They should be independent of each other. That's the only condition. So they will be independent of each other. These are properties. And see, we can describe any Cartesian coordinates x1 in the terms of q1, q2, q1, y1 will be in terms of z1, z2, and there are n particles, then x and y and n will be represented by these coordinates, and they are independent of each other. We can write them in this form also, means partial derivative of q1 with respect to q2 will be 0, because q1 is independent of q2, and it can be written in the form of Kronecker delta, because qi is independent of qj. So if they are not equal, I is not equal to j, then this will be 0, and if they are equal, it will be 1. So this is the property of Kronecker delta. Now see, we already discussed these systems, holonomic and non-holonomic. Let's see them one more time, because now we have more information. Any system in which all the constraints involved are holonomic in nature is called holonomic systems. So constraints should be holonomic, then we will say that the system is holonomic system. And in holonomic system, degree of freedom can be calculated by 3n minus k, and each constraint reduce the one independent variable. From here we can see one holonomic constant eliminates the requirement of one independent variable. So required independent variables will be 3n minus k. So number of generalized coordinates is nothing but 3n minus k. So we denote this term as small n, that is degree of freedom. So remember this, how to find the number of generalized coordinates, that is n, and that is degree of freedom. We already discussed 14 examples for how to find the degree of freedom for different systems. So remember that. Now see, non-holonomic systems. We already discussed what are non-holonomic. When the constraints are not definite, means something like this. This is a sphere and there is gas inside. So every particle's distance from the center will be less than r. So this is kind of condition which is not definite. So we call these systems as non-holonomic. And even this is non-holonomic because this is not fixed, not definite. This is a range. So these are the non-holonomic systems. And spring system also, this was a non-holonomic system. So what is the meaning of this? These systems are not able to, means they don't have the ability to reduce the one independent variable. So any system which has at least one non-holonomic constant is called non-holonomic system. A non-holonomic system can have both types of constants, k, number of holonomic constants, and k dash number of non-holonomic constants. So even one non-holonomic constant is present, then we call that system as non-holonomic. So total degree of freedom will be 3n minus k dash, because this non-holonomic constant, even applying some restrictions, so it is reducing degree of freedoms, but it can't reduce the independent variables. So it won't reduce the generalized coordinates, but it will reduce the degree of freedom. So degree of freedom will be this, but the generalized coordinates will be 3n minus k only. Means only the definite holonomic constants can reduce the independent variables. So for the non-holonomic system, this n is always greater than the degree of freedom. I hope you get this point, because these k dash can't reduce the requirement of independent variables, and that's why n will be 3n minus k only, always. Now see, we know what are generalized coordinates and how many generalized coordinates we will have that are depending on the degree of freedoms and what kind of system we are having that are depending on that. Now see, if the generalized coordinate is changing with time, okay, means we are having a complete system described by this one point, and means these coordinates, then these coordinates are changing with time, means because whole the system is evolving. So any coordinate changing with time can be represented by the generalized velocity. We call this generalized velocity, that is generalized coordinate changing with time. This is generalized velocity. Now see, these are also independent of each other, means q1 is totally independent of q1 dot. So if you find the derivative of del q1 dot divided by del q1, so you will get again 0. So that is a very interesting property of these coordinates, because every coordinates we are getting will be independent of each other. So this will also independent of this will independent of this, and together they are independent. So total time derivative of a generalized coordinate is called a generalized velocity. In Lagrangian and Hamiltonian formulation, generalized coordinates and velocities are considered independent of each other. See, del q1 dot is independent of del qj, because this is equal to 0 for all, whether it is I equal to j, it will be independent of each other. That's what I told you here. I is not equal to j, whether it is I equal to j. Now configurational space. Now when you have the degree of freedoms and you know how much generalized coordinates we require, so it is small n, so we'll create a n dimensional space. N dimensional space is called the configurational space. Now here these n dimensions represent the each independent coordinate okay, generalized coordinate. So this is a n dimensional space that is made up of all qi and is used to represent the dynamics of a system in Lagrangian formulations. At any time t, the state of the system may be represented by a single point in configurational space. Now see, let's see an example. We have 3, means here we get these 2 degree of freedoms, okay, so only 2 dimensional space we required. So at any time we just required a single point which will describe this motion of all the system, because we know, means only the 2 degree of freedoms, means only 2 coordinates required to describe the system. So at any point we can describe the system at any time, okay, and whether it is 6 or 7, means let's say here we have this system, so degree of freedom is 6, so we have 6 dimensional space, and each point describes the system at any time, okay, means these variables will be on the independent axes and a single point can describe the system at any time. With time the system will change and these whole system of coordinates will change. So we'll see in the configuration space how it works. So time evolution of a system is represented by a curve in configurational space. Here curve means sequence of different states of the system at different times. Now I will tell you in the next page this will be more clear here now. Now see, first we see what is the difference between these two spaces. See, this is a real space, okay, and you have n particles in a system. So each particle have 3 coordinates. So this will have 3 coordinates, this will have 3 coordinates, this will have 3 coordinates. So you will have 3n number of independent means 3n number of coordinates here, okay, for a n particles. Now see, they are already very messy. Now if they are changing with time, each coordinates of each particle are changing with time. So this will go like this, changing coordinates, this will go like this, this will go like this, this will go like this. If there are too large number of particles, then they will be a messy situation and it is very difficult to handle. Here we need to know the evolution of 3 in Cartesian coordinates with time, and it is a very difficult task because you can't see what is happening here because this will be very messy. Now see what we do. We find the degree of freedoms, means the minimum amount of independent variable required to describe the system. So let's say we get n number of independent variables required. So we will create an n dimensional space now. N dimensional space we created and we plotted with time. So at any time, these whole system will be represented by a single point. Means x1, x2, y3, x2, y2, y3, x3, y3, means all are represented by on the different axes. Means we have n dimensional space and 5 degree of freedoms are required to describe the system. Then we will have 5 coordinates for each particle. So only a single point required to describe all the system. Now these are changing with time. So these are also changing with time. Means now these are here for this point is here, for this point is here, for this point is here. So now these all points will be represented by a single point. So now this whole system moves toward this another point where this whole system is represented by this another point. And with time this is evolving like this. This whole system is going to S2 state, will be represented by a single line curve in this configurational space. So hope you are getting this point. This is very interesting and a little bit tricky to understand. Now we have n dimensional space and this whole system represented by a single point, and with time this single line can represent this evolution which is evolving in these directions. Okay, so only single line can represent this whole evolution. So see, k constants we have, so required number of generalized coordinates will be n. So n dimensional space we will create and they are independent of each other and orthogonal to each other. So we have n axes and we can represent a single point for these whole system. Okay, so n dimensional space having n orthogonal axes. Now this is the evolution with time. The whole system is moving to S1 to S2. So it can be represented by a single line in this configurational space. This is called the configurational space, and this can move from here to here also, and it can take this path also and this path also. There are infinite ways to take the paths. Now the question is which path system will follow in moving from S1 to S2, as there are infinite number of ways possible between S1 and S2. So this question is answered by Hamilton's equation. Means this question was answered by the Hamilton in terms of least action principle. So Hamilton gives this answer that which path it will take. Okay, so we will study more about this in the next lecture. If you are having doubt, then please put in the comment section. I will try to resolve. But without understanding this, don't move forward. That's all. Thank you everyone.